Welcome back, everybody. I am really excited about what we're going to be talking about today. We are finally, finally at what's going to feel like calculus. Now, maybe it's a part of calculus you didn't like very much because lots of people have trouble when they get to calculus 2 and they deal with things like sequences and especially series and trying to understand how all that fits together. And so I think going through this will help you solidify some of those ideas from calculus, but much more importantly, explain what's really going on in all of that. So all the stuff we've been doing this entire time has been leading up to today. This is it. This is what we've been working so hard to do is to get to this sequence of lectures, pun intended, where we finally learn about sequences and what that means. So this is the sort of putting everything together and doing some calculus. Okay, so let's get started. What's a sequence? So here's our technical formal definition of what a sequence is. A sequence is a function whose domain is n, the natural numbers. Okay, so that's a great definition for our purposes because we're all smart enough we know what all these words mean, right? We know what functions are, we know what the domain of a function is, if you think about what does it mean if the domain is the set of natural numbers, well, that means that we're plugging in to this function numbers like 1, 2, 3, 4, 5, 6, and so on, and nothing in between. See, it doesn't make sense to plug in a number like pi or 3 over 2. The domain is just the numbers 1, 2, 3, 4, 5, 6, and on to infinity. So if you think about that for a second, we've seen that before when we were talking about cardinality, when we were talking about counting. Those are the numbers, the counting numbers. Those are the numbers that we use when we count things. So what a sequence really is, it's a function where you plug in a 1 and you get something back. You plug in a 2 and you get something back. In other words, there's such a thing as a first thing. That's what you get when you plug in 1. There's such a thing as a second thing. That's what you get when you plug in 2. There's a third thing, and it's what you get when you plug in 3, and so on. So this is a great definition because it ties, the idea of a sequence to stuff we really understand, like functions. Now, of course, when I teach this to students, and I'm doing this in calculus too, and they've seen sequences for the first time, I always tell them this is my informal definition, right? So if I ask you what a sequence is on an exam, I want the previous slide that a sequence is a function whose domain is the natural numbers. But maybe the right way to teach this to a calculus class, especially when they see it for the first time, you tell them that a sequence is a list. Okay, it's a list of numbers or a list of something, right? Because we're having a first thing, a second thing, a third thing, and so on. So it's really just like having a list of numbers. And of course, when it gets interesting is when that list seems to be going somewhere, right? Okay, so for notation, you'll see lots of different notation. What our book uses is parentheses and then s sub n. Now, okay, this takes a little reminding. People are probably used to seeing s sub n. You've probably seen s1, s2, s3, or maybe your calculus book used like a1 or a2 or a3 and so forth. Um, the letter doesn't matter so much. It's the fact that for sequences we often use this subscript with an n. So you'd have like again like an a1 or an s2 and so on. So that's because we can think of this like a list instead of writing it like we normally would a function where you might write f parentheses 1 parentheses like f of 1 or f of 2 or f of 3 in normal function notation. Because we're really in the back of our mind thinking of this like a list, then we'd have like a first S and a second S and a third S. So we just call them S1, S2, S3, and so on. And if we have to say the whole thing instead of writing down a function like F, because we're thinking of these as like S1, S2, S3, we just, up to Sn, right? Where n is our variable that we're plugging in now, we write this as S sub n, and maybe we put parentheses around it to denote that it's a whole list. Sometimes you'll see people put brackets around it like a set, but then that's confusing because it almost makes it look like a set. Right? Sometimes people will write something like this, where they put n equals 1 or n equals m, some number, up to infinity. That kind of looks like a series, and it's, related obviously to that, right? We usually will drop the the n equals m to infinity stuff and just write parentheses around the name of our sequence, because obviously we're interested in what happens when the sequence goes somewhere. As n gets bigger and bigger and bigger, what happens to the s sub n? So maybe this helps to explain sort of what I mean by going somewhere and how that's going to work. You can graph a sequence, because remember, it's a function. Its domain is the natural numbers. So I could literally graph it. So when x is 1, I get a value of the sequence and I plot it there. When x is 2, or n is 2, right, I get s2, my second value, and I plot that on the y-axis. Right? And so I get a third number and a fourth number and so on. And of course, you can see that what's happening in is my index n is going to the right, and the value of the sequence is of course going up and down as it changes. So the y-axis is denoting the value of my sequence, and as I move to the right, then the value of the sequence changes. Right? So what do I mean by a sequence going somewhere? Well, if you look at this picture, it's starting to look a whole lot like that sequence is leveling out. I mean, like a horizontal asymptote is what we'd call it if we were doing, algebra. Right? It looks like that those dots are all kind of getting closer and closer to each other, and closer to, some sort of a, well, the right word is limit. Right? So there's looks like there's some sort of, again, like a horizontal asymptote, some number s that all those dots are getting closer and closer and closer to. This is a great picture to have in mind, and we'll come back to this um, in just a second when we formally define what we mean by a limit. But this is exactly the idea of what the limit of a sequence does. It's not usually the picture I have in my head, though. So let me show you the picture that I usually have in my head. So these numbers, S1, S2, S3, and so forth, those are real numbers. They live on the number line. So what I usually see in my head is a picture like this. So there's S1. It just sort of pops up on the number line. And then there's an S2. And then there's an S3 and an S4. And there's, S5 is way over there to the left there. And so on. And so these numbers just keep sort of popping up on the number line. Now, the disadvantage to thinking of sequences this way, of course, is if I just stopped here and I just showed you that picture and I didn't show it to you, over time, you wouldn't know which one was first, which one was second. So when I say I see this picture in my head, it's like I'm watching a movie, like I'm playing for you now. I'm watching them pop up one after the other after the other. So then I know which one is first and which one is second, and so on. Okay? And of course, it looks like they're all getting closer and closer, and they're clustering around some number, right? They're accumulating around some point, which, of course, the connection between sequences and what we have called accumulation points will become very obvious as we go a little further into this. They're all sort of accumulating there around some number s, right? They seem to be getting closer and closer to s as time goes on, right? So this is a great picture to keep in your head. Right? Okay, so I think we need some examples with a sequence, that we can sort of sink our teeth into more than just watching the pictures. So here's an example. This is a standard sort of example you might see in a calculus 2 class, right? Maybe the very first thing you talk about is a sequence like 1 over n. Okay? Obviously, 1 over n converges to 0. Right? Why? Well, the idea is when n gets big, then 1 over n gets small. So what I would tell a group of Calculus 2 students is, suppose that n were a billion. And I always, when I say that, take a step back away from the class, because the next thing I say is, if n is a billion, then of course 1 over n would be 1 over a billion, which is a billionth. And I deliberately make a big deal of the th when I say that, and then I usually say, see, I step back so I wouldn't spit on you on the front row, and everybody laughs and smiles. So, but that gets the point across, though, right? It breaks the tension just a little bit, because we're doing something that's very, very serious in this section, and very stressful for the students. And they tend to remember this idea that 1 over something big is really something small, right? It's a number very close to 0. So if I start plugging in larger and larger numbers for n, then 1 over n will get closer and closer to 0. And when I'm teaching Calculus 2 for a general sort of population, that's about as much detail as I go into with them. With the way that works. Now we obviously, are trying to understand the theory behind calculus and what really that means, right? What does that mean by getting closer and closer, and what does it mean to say this is going somewhere? And we're going to have a real definition, right, of exactly what that means in just a few minutes. But if I were doing this with just a regular freshman calculus class, you know, that's the most important idea I want to get across to them at the very beginning. That when n gets big, 1 over n gets really small. And then I would talk about what I always call the tower of power, right? And so it took me a long time to figure out how to get my slides to do this. So here's my tower. Ready? It's gonna. There we go. It builds up brick by brick by brick as it goes up. See, blue bricks rising into the sky, and so as the tower rises higher and higher, each brick is more powerful than the brick below. So, for example, I might start by talking about n, which is kind of in the middle there, or near the middle. So n, it goes off to infinity like n. In other words, if I think about the sequence n, that's just counting, the first thing is, well, when n is 1, I get 1. When n is 2, the sequence is 2. When n is 3, the sequence is 3. It's really boring. The sequence really goes 1, 2, 3, 4, 5, 6. Okay. What about n squared? That has a little bit more power to it. It's a brick higher. What happens to n squared? Well, instead of going 1, 2, 3, it goes 1, then 2 squared, which would be 4, then 3 squared, which would be 9, then 4 squared would be 16, and so on. So you can see it goes off to infinity much faster, because instead of going 1, 2, 3, 4, it goes 1, 4, 9, 16, 25, and so on. Of course, n cubed would be even more powerful. N to the fourth would be even more powerful. N to the 100th would be even more powerful. And eventually, you get to things that are even more powerful than n raised to a power. That's exponential functions like e to the n or 3 to the n. Of course, 4 to the n would be even bigger. And even more powerful than exponential functions are things like, if I were doing this in class, I'd yell really loud, "N!" really loud with the exclamation point. Of course, that's not a very excited N who's yelling. That's n factorial, right? So that would be n times n minus 1, the next smallest number, times n minus 2, and then all the way on down. Like 7 factorial would be 7 times 6 times 5 times 4 times 3 times 2 times 1, all the way down. That's bigger than any of the exponential functions. But even bigger than n factorial would be n raised to the nth power. Okay? And of course, you could keep going higher up the tower. There's obviously functions that grow even faster than that. And there's functions that grow slow too, right? Like square root of n. That will go off to infinity, but it goes very slowly. So you would have like square root of 1, and then square root of 2, and square root of 3, and square root of 4. Well, square root of 4 is just 2, right? You'd have to get up to square root of 9 before you actually get to 3, right? So then of course you might have a third root or a fourth root, which will grow even slower, and then something like a logarithm, which of course is the inverse function for an exponential, because the inverse function grows even slower, but it still does go off to infinity eventually, right? Those of 1, log of 2, log of 3, log of 4, those numbers all get bigger and bigger and bigger. They just get bigger really, really, really slowly. So eventually, log of n will become unbounded and get as big as you want it to get, but you have to plug in a really big number in order to get log of a big number to be big. Okay, so how does that work if I were just doing just a regular straight calculus 2 example? I would show someone, a sequence like this, and I'd say, well, look, we've got 3n squared plus 4 over n squared plus 5n in the bottom. So what's going on is there's an n squared plus some stuff in the top and the bottom, right? The 4 hardly matters. If n is equal to a billion, then when you square it and add 4 to it, you hardly even notice it. And even that 5n, right? If n is equal to a billion, n squared is so much bigger than even 5 billion that you hardly even notice it. So all that really matters, because of the tower of power, is in the top is really the n squared as far as determining the power goes. And the most powerful thing in the bottom is the n squared. So it's not like you can cancel off the 4 and the 5n. But if you plugged in a ginormous number, you can just try this with your calculator at home. Pause the video for a second if you don't believe me and just try plugging in a billion into this this function, right, to see what the billionth term would be, um, what you'll see is it'll be really close to 3, because this is a lot like saying that you have 3n squared over n squared, because the 4 and the 5n hardly matter when you start plugging in such huge numbers, because n squared is so much more powerful, my tower of power. So the uh, the n squared in the top and the n squared in the bottom essentially tie on the tower of power, and so you get, well, it's like the n squares would cancel, although they don't literally algebraically, but what you get is something very close, and that's exactly what you'd expect to do if we're talking about a limit, is we just want to get close. Okay, what if I change that n squared that was in the numerator, now it's a red n cubed, right? So now, of course, the n cubed is much more powerful than the n squared that's in the bottom. So the top is much larger. So as I plug in big numbers, I get a bigger and bigger number out. Because when the top is big, it makes the whole thing big. So this, of course, is going to diverge off to infinity. And if I change that n squared in the bottom to like a red n to the sixth power, well, now my most powerful thing on the board is the n to the sixth. It's in the denominator, and when you have, remember, a big number in the denominator, well, it's going to make the whole thing small. So this is all going to converge to 0. So again, this is all sort of calculus 2 review stuff. You may not have thought about this for a long time, and you may want to rewatch the last 3 minutes or so here to make sure that you're clear on how all of this works. Because, of course, what you'll see in the homework will very, very, very many sequences like this where it'll say, okay, find out what this converges to, which is really just looking at it, you can tell, and then prove that it converges to that. Because you think about this for a second. So far, all I've done is sort of hand waving, and I've muttered something about a tower, right? And you know, when you look at this, how do I really know that in the 3n squared plus 4 over n to the 6 plus 5n, that this sequence really does converge to 0? I mean, how do I know that if I listed out all those terms, they would all be getting closer and closer and closer to 0? And even if I just listed out the first billion of them, okay, and had my calculator graph it for me or something, I mean, you'd be able to see that it looks like it's all getting really close to 0. But that's not a proof, right? I mean, I don't know that this doesn't just suddenly decide to jump up and run off to infinity later. Right? There are sequences that do converge to things so slowly that if you tried to plot the first billion terms, you wouldn't really even be able to tell where it was going just from the picture. So we need a way to be very precise, very formal, and really know what it means for something to converge. And that's where our definition comes in. We're going to have a real definition of what it means for something to converge. And that will be the subject of our next video.